Welcome to the December issue of AJP-Heart and Circulatory Physiology from the editor's desk. Gino and I want to tell you about a great issue this month. We have lots of great research, and I think if you go to our website and look at our new review articles and the great new science, that's right, tell the people how wonderful this month's science is. Absolutely, Gino, and we're going to really have a great month of reading good cardiovascular science. So let's get started. So let's take a bird's eye view. First review, Toldo et al. Review strategies inhibiting, priming, triggering, or caspase-1 activity or blockade of the inflammasome-related cytokines interleukin-1b and interleukin-18, focusing on the beneficial effects in experimental models of acute myocardial infarction in animals and the initial results of clinical translational research trials. Review by Pabidi et al. The authors summarized sex differences in vascular function and the role of 17-beta-estradiol, the higher incidence of cardiovascular disease, and the failure of hormone replacement therapy in postmenopausal aged women could be partly associated with fundamental differences in the vascular structure and function between men and women and between pre- and postmenopausal women, respectively. The female sex hormone 17-beta-estradiol regulates the majority of these mechanisms. Law et al. Tested the hypothesis that enhanced cardiac calcium cycling would remediate cardiomyopathy caused by dystrophin deficiency. They used a genetic complementation model approach by crossing dystrophin-deficient MDX mice with PLN knockout mice. As expected, adult cardiomyocytes isolated from double knockout mice exhibited increased contractility and faster relaxation associated with increased calcium transient peak height and faster calcium decay rate compared with control mice. However, compared with wild-type MDX and PLN-KO knockout mice, double knockout mice unexpectedly had reduced in vivo systolic and diastolic function as measured by echocardiography. Despite enhanced intracellular calcium handling at the myocyte level, Duchenne muscular dystrophic cardiomyopathy was exacerbated owing to unregulated chronic increases in calcium cycling in DKO mice in vivo. Sadek et al. Hypothesized that as the myocardium reacts and remodels to ischemic injury over time, there is an analogous sequence of gene expression changes in the thoracic spinal cord, dorsal horn, the processing center for incoming afferent fibers from the heart to the central nervous system. Acute and chronic myocardial ischemia was induced in a large animal model of Yorkshire pigs, and the thoracic dorsal horn of treated pigs, along with control non-ischemic pigs, was harvested for transcriptome analysis. They identified 32 differentially expressed genes between healthy and acute ischemia cohorts and 46 differentially expressed genes between healthy and chronic ischemia cohorts. The canonical immediate early gene CFOS was upregulated after acute MI, along with FOSB dual specificity phosphate 1 and 2 and early growth response 2. After chronic MI, there was a persistent yet unique activation of immediate early genes, including FOSB, nuclear receptor subfamily 4, group A members 1 through 3, EGR3, and TNF-alpha induced protein 3. In addition, differentially expressed genes from chronic MI signature were enriched in pathways linked to apoptosis, immune regulation, and the stress response. Little is known about vascular mitochondrial respiratory function and the impact of age. Therefore, Park et al. Studied skeletal muscle feed arteries from young, middle-aged, and old subjects and mitochondrial respiration, as well as citrate synthase activity. Complex 1 and complex 1 and 2 state 3 respiration were greater in young than middle-aged and old subjects, and, as in the case of complex 2, state 3 respiration were inversely correlated with age. In contrast, state 4 respiration and mitochondria-specific superoxide levels were not different across groups. Similarly, superoxide citrate synthase levels were lower in young than old subjects and correlated with age. Therefore, with aging, vascular mitochondrial respiratory function declines, predominantly as a consequence of falling mitochondrial content. However, per mitochondrion, aging likely results in greater mitochondrial-derived oxidative stress, which may contribute to age-related vascular dysfunction. Thank you for watching this month's installment of From the Editor's Desk. On behalf of our staff, associate and consulting editors, and the APS, we wish you a happy and healthy holiday season and new year. We look forward to your submissions in the coming year, and be sure to send us your best work now.